Geologists and paleontologists, people who study the Earth and ancient life, divide up Earth history using what is called the geologic timescale. The biggest blocks of time are called eons, which lasted for hundreds of millions of years to billions of years each. The first three eons together, the Hadean, Archean, and Proterozoic eons, make up what is called the Precambrian, which lasted from the formation of the Earth 4.6 billion years ago until about 539 million years ago. For nearly this entire stretch of time, life consisted almost entirely of single-celled organisms living in the oceans, and complex animal life didn't appear in the oceans until the last couple hundred million years of the Precambrian. The fourth eon, the Phanerozoic, is when most of the interesting stuff happens. The Phanerozoic eon is divided up into three smaller chunks of time called eras, which last for tens to hundreds of millions of years each, the Paleozoic, Mesozoic, and Cenozoic eras. Each era is divided up in turn into smaller chunks of time called periods. During the Paleozoic era, which lasted from 539 to 252 million years ago, life continued to evolve in the oceans, but it also moved on to land for the first time, giving us the first land plants, land invertebrates like insects and spiders, and the first backboned animals with legs. The first large land animals evolved toward the end of the Paleozoic. During the Mesozoic era, which lasted from 252 to 66 million years ago, dinosaurs and other large reptiles dominated the land and the seas, and many groups of familiar living things appeared for the first time, including the first flowering plants, mammals, crocodiles, frogs, salamanders, lizards, and snakes. The extinction of the dinosaurs about 66 million years ago marked the beginning of the Cenozoic era, which we are still living in today. During the Cenozoic, mammals took over as the dominant land animals, grasslands became common for the first time, the climate cooled considerably, and humans and other primates appeared. This is a hugely simplified summary, but those are some of the popular highlights. So how do we know all this? How do geologists and paleontologists reconstruct the history of life? When we look at the fossil record, how do we know the order that organisms lived in? Which ones coexisted and which were separated by millions of years? How do we know, for example, that showing dinosaurs and humans coexisting is fiction? There are many different types of rocks making up the Earth's crust. Most of them are igneous rocks, which form from molten rock or magma, cooling underground to form rocks with large crystals like granite or diorite, or erupting on the surface to form volcanic rocks like basalt, pumice, and tuff. Metamorphic rocks are altered by heat and pressure, but not enough to melt them. Although igneous and metamorphic rocks make up most of the Earth's crust, neither usually contain fossils, the remains of ancient organisms. The heat involved in the formation of igneous and metamorphic rocks is usually enough to destroy the remains of living things. The type of rocks that fossils are usually found in are sedimentary rocks. These rocks started off as sediments, such as sand, gravel, and mud, the busted-up residue of other rocks. Rocks exposed on the Earth's surface are weathered by water and atmospheric gases. The minerals in these rocks are physically broken down into finer and finer pieces, chemically converted to new minerals, and even partly dissolved. These sediments can then be transported. They are sometimes carried by the wind or within glaciers. However, most sediment transport occurs in water. Rivers and streams can carry sediments for thousands of miles and then deposit or lay them down in all kinds of different settings. On land, sediments are commonly deposited along the banks of rivers or out in the surrounding floodplain during flooding. When rivers reach bodies of water like lakes and seas, their sediment loads can get dumped off there, piling up on the bottom as layers of mud. The dissolved components of the source rocks can combine to form new sediments such as carbonates and evaporites, or are used by living things to make hard shells, which can also form layers when the remains of those animals build up on the seafloor. Coal is another type of sedimentary rock formed by the breakdown of dead plant material. Occasionally, the remains of dead animals, plants, and other organisms are buried in sediments and can become fossils. Over time, as sediments are compacted by the weight of more and more sediments and infiltrated by minerals left by groundwater, they are hardened into rock. In all of the varied environments where sediments are deposited, sediments can pile up at some times and get washed away in others, destroying part of the sedimentary rock record. However, if sediments are allowed to pile up, more or less undisturbed, for long enough, sediments can form tall stacks of layered sedimentary rocks called strata. In some places, these layers of strata are uplifted by geological forces and eroded again, as is happening, for example, in the western United States. Over millennia, rainwater washing over the strata can carve out the modern-day topography so that geologists can study them and search the eroding layers for the fossils buried in them. It's a bit like if you made a cake, layer by layer, and then allowed a hungry toddler to rip into it, removing handfuls of cake until only mesas and cliffs of cake were left, exposing the layers of cake that you had carefully built up. Erosion destroys rocks and fossils, but we would have a hard time studying rocks and fossils without it. The study of rock layers is called stratigraphy. We notice that layers of strata differ from each other, being made of different sedimentary rocks, like sandstone, mudstone, and carbonate rocks like limestone. Thick sequences of strata that differ in some way from those below and above are referred to as groups or formations, and these are usually divided up in turn into smaller packages of sediment called members or beds. It is on stacks of layered sediment like this that we can start reconstructing the history of the Earth. Let's start with the basics, just looking at one spot where the sedimentary rock record is exposed. We'll refer to this one spot as a stratigraphic section. When these layers of sediment formed, they were piled on top of each other over time. This means that the layers on the bottom are oldest and they get younger going up, with the layers on the top being youngest. This is therefore also true of any fossils buried in those layers. Fossils in the lower layers are older, and those in the higher layers are younger. This is called the principle of superposition, and it's the foundation for reconstructing Earth history. Again, think of our cake in the order we stack the layers in. So right off the bat, we've begun to put together a history, at least for this one spot. We've figured out the order that the sedimentary rock layers formed in, which is called lithostratigraphy, and we've also worked out the order that the fossils appeared in, which is called biostratigraphy. However, how old are these rocks and fossils compared to rocks and fossils in other areas? Let's start with the immediate area right around our first section. We can trace these exposed layers of rock for several miles, with that same capping gray sandstone forming the top of the cliffs throughout the area. Here's a nearby cliff in which we can see the same layers as in the first section. The lower orange sandstone, the reddish mudstone above it, and the capping gray sandstone. Identifying equivalent layers of sedimentary rock at different locations like this is called lithostratigraphic correlation. This correlation allows us to combine information from fossils collected at both spots to get a more complete biostratigraphy and to begin to determine the ranges of these fossils, the length of time over which the animals existed. Let's say that at our first section, we found this orange skull in the orange sandstone and the gray skull in the gray sandstone. At the second section, we find these same types of fossils but in the reddish mudstone. Lithostratigraphic correlation tells us that these fossils in the second section are younger than the orange skull on the left, but older than the gray skull on the left. By combining this information, we begin to determine the ranges of these fossils. The orange skull fossil appeared first before the gray skull fossil, but coexisted with it for a while before disappearing. Then the gray skull fossil continued to exist after the orange skull fossil was gone. This is just a start. Finding new fossils may change our understanding of these ranges. We could, for example, find an orange skull in the gray sandstone and a gray skull in the orange sandstone, telling us that these animals actually coexisted for the entire time. It may take a lot of fossil collecting for many years before we can really start to feel confident that the ranges we see in the rock record are actual representations of how long the animals lived. The strata above the gray sandstone have been removed by erosion in these first two sections, but we can trace this gray sandstone for several miles. If we do so, we come to a place where the strata immediately above are preserved. Here we find a section of mud and sand capped by another gray sandstone. These layers are, of course, younger than the lower gray sandstone, and much younger than the layers below that. The same goes for any fossils we find in those layers, allowing us to add more biostratigraphic range information. Individual beds like this can usually only be traced for short distances, anywhere from tens of feet to tens of miles, but we can often correlate bigger packages of sediment like groups, formations, or members for hundreds of miles. So lithostratigraphic correlation can be applied to rock layers and fossils over big distances. By using lithostratigraphic correlation to stitch together fossils found in different layers in different places, we can start to put together a history of life that covers the entire region. Eventually, we might be able to do something like this, putting together a simplified geologic history of western Texas over the past 300 million years, showing how fauna has changed over time. Here's another composite section for Mesozoic rocks in southern Utah, assembled in the same way, showing changing dinosaur faunas. Obviously, this section includes a lot more information than I included in the very simplified section for Texas. That's a good start, but we also want to know the relative ages of fossils all over the world so we can put together a detailed history of life for the entire planet. For example, if we have this sequence of fossils in Texas and another sequence of fossils in South America or Europe, how do we know their relative ages? Are they the same age? Are some sections older than others? Here we run into a problem. We can't use the same method of lithostratigraphic correlation to connect rocks all over the world because individual sedimentary formations don't usually extend that far. If you follow them far enough, rock layers thin out to nothing, or they're cut off by erosion, or they become buried under soil. Lithostratigraphic correlation can only take us so far. How then do we determine the ages of different formations so far apart geographically that lithostratigraphic correlation doesn't work? It turns out that the fossils found in sedimentary rocks can help us, because living things can move between different environments. So the remains of the same type of animal or plant might become buried in different formations, even in different parts of the world. This is something that geologists figured out in the 19th century. In the early 1800s, geologists recognized that the same sedimentary formations occurred throughout the British Isles, and they always occurred in the same sequence. Moreover, within Britain, a given formation always contained the same fossils everywhere they found these rocks. However, as geologists examined other parts of the world, they found different sedimentary formations, but these strata often contained the same kinds of fossils as in Britain, and in the same sequence. This allowed geologists to build a history of life covering the entire Earth. Here's how it works. Here are two sections in different parts of the world. They don't have the same sedimentary formations, but they do have the same fossils and occurring in the same sequence. We know that within each section, these fossils are older than these fossils. By marking the levels where different fossils appear and disappear, we can divide up the sections into these blocks of strata called biozones, and then we can correlate these biozones between sections. This process is called biostratigraphic correlation instead of lithostratigraphic correlation because we're using fossils instead of rock types to tie the sections together. If we make the assumption that layers with the same fossil are the same age in different places, then we know the relative ages of layers between areas. This layer is older than this one. But now let's look at two other sections that don't have any formations or fossils in common. At first, we would have absolutely no idea which section is older and which is younger, until we notice that these two sections share fossils with the first two sections. This section shares the red snails, and this section shares the blue oysters. By correlating all four sections using biostratigraphy, we now know that this section is younger than this section, and these four sections have now been stitched together to create a composite biostratigraphy, not just for a particular area, but for several different parts of the world. We begin to put together a history of life that spans the entire Earth, dividing up Earth history using fossils. This process is how the geologic timescale was constructed in the 19th century. Geologists realized that rocks all over the world could be tied together in just this way by combining basic superposition with lithostratigraphic correlation on local scales and biostratigraphic correlation on bigger scales. Well before the beginning of the 20th century, geologists understood the big picture of Earth history. When you look at the geologic timescale, those blocks of time like eras and periods we discussed were originally biozones. It isn't a coincidence that major events like mass extinctions, where lots of species go extinct at once and are replaced by newly evolved species, just happen to fall at the boundaries between periods and eras. Those changes in the fossil record are how those units of time were divided up in the first place. By the early 20th century, paleontologists knew the order in which living things appeared. However, they still had no idea exactly how old rocks and fossils were. Where do those numbers on the geologic timescale come from? We will discuss this and other complications to building the history of life in a future video. Thanks for watching.